This is Physics 241 Laboratory. This is lab number 4. Today we're going to do gravity on an incline. As you know, in previous labs we've dropped balls and we found when an object falls straight down, the acceleration due to gravity is 9.8 meters per second squared. We also know that if we have a cart just in a flat position and it's not moving, that there's no gravity exerted on it. The gravity in this scenario going in this direction would be 0. So if we know straight down it's 9.8 and flat it's 0, what about on an angle? If we have a cart on an angle. And what we'll do in today's lab is we'll set up a cart on a rail, and we'll prop the rail up so that the cart's going to be riding down on an angle. And we're going to have a motion detector looking at the cart and tracking the cart, and the motion detector will be hooked up to our computer and we'll be able to generate d over t and v over t graphs based on the motion of the cart. And what we're trying to find out is what's the gravitational pull or the acceleration due to gravity when a cart is on an angle. And I think we'll find that the mathematical formula will be the acceleration of the cart on an angle is going to be g, which is 9.8, times the sine of the angle involved. And again, building off that, our cart ramps are 121 centimeters long. And we're going to prop it up, the ramp up a certain height. And of course, knowing simple trigonometry, the sine of that theta angle is h over the hypotenuse, this height over 121. So what we're going to do initially is calculate what A is going to be based on this formula, and then we're going to do 5 trials of runs of running a cart down that ramp and measure it using the motion detector. And we're going to compare our calculated acceleration to our measured acceleration. And we have 5 specified heights in centimeters: 2.74, 5.18, 6.97, 9.20, and 11.5 centimeters. That's what we're going to do. Each one of the 5 trials will be at this height. And that corresponds to this angle. It's a very gradual angle, no more than about 5.5 degrees. If we take the sine of that angle, we come up with this number. And if we multiply the sine of that angle by 9.8, we're going to come up with our calculated acceleration due to gravity. And as you can see, it's going to range from 0.22 to 0.92. In other words, when a body's falling straight down, it's 9.8. When it's on an angle, up to about 5 degrees, we're talking about 0.9 meters per second squared. So in all these scenarios, the acceleration due to gravity is going to be about less than 10% of the normal dropping of gravity. In order to measure that acceleration, we're going to generate d and v graphs, dt and vt graphs on our computer using the Vernier software. Again, we'll generate curves of d over t and v over t based on running the cart down the ramp. And using our linear fit function, we're going to measure the slope of this velocity over time. As you can see, this is as it goes down the cart and this is as it hits the bottom. Knowing this slope will tell us the acceleration due to gravity. And if we go through that process, and as you can see here in the red, this is what the linear fit measure from the computer would give us. These numbers, 0.22, 0.427, 571,753,922. And we can compare these measured figures to what we calculated. And as you can see, they are very close. When we did do the measurement, we did 3 trials each to make sure that it repeated. And our error was somewhere less than 3%. So we have good correlation between our measured results and our calculated results. So our conclusions from this lab are that in coming up with the procedure we have, we were able to determine that the acceleration due to gravity that we measured was pretty much equal to the acceleration due to gravity that was calculated. We also determined that gravity, when the incline is less than a 30-degree angle, is going to be just a fraction of the 9.8 meters per second squared. And this is rather a realistic expectation because all of our trials were at less than a 5-degree slope, and normal roads would be in that category. And that concludes Lab 4.